Hello everyone, welcome to this lecture in the Build Large Language Models from Scratch series. In today's lecture, we are going to look at one specific component of the large language model architecture, and that is layer normalization. Before that, let me quickly recap what we covered in the last lecture. In the last lecture, we essentially had a bird's eye view of how the LLM architecture looks like. So what we are going to do is that the LLM architecture consists of several components which are arranged together. In the previous lecture, we constructed this GPT backbone, which is like a dummy class which will hold all these components. The first component is the layer normalization, JLU activation, then the feed forward neural network, and then shortcut connections. These four components make up the transformer block, which is one of the key components of the entire GPT architecture. So let me show you how this looks like. So if you zoom into the transformer block, you will see that the transformer block has a number of layers which are stacked together. You have a layer normalization followed by the mask multi-head attention layer, followed by the dropout layer. You have the shortcut connections, then another layer normalization, a feed forward neural network, dropout layer, and then another shortcut connections, etc. If you zoom into the feed forward neural network, you will see that it consists of linear neural network layers along with the JLU activation function. All of these are stacked together in a format which looks something like this. So let me take you to the broadest level view. Looks something like this. So you have the input text which you tokenize, then you pass it into the GPT model. In the GPT model, we first do the token embedding, then add the positional embedding vectors, pass these input embeddings to the transformer block. Within the transformer block, it goes through all the layers which I just showed you, and then we have the output layers, which essentially decode the output from the transformer block, and we predict the next word from the input. This is what happens inside the GPT architecture. And we are going to start looking at every single component of this GPT architecture. Today, we are going to look at this component which is called as layer normalization. So if you look at layer normalization, it actually comes up at multiple places. Within the transformer block itself, if you see, before the multi-head attention, we have a layer normalization. After the multi-head attention, also we have a layer normalization. So the layer normalization comes within the transformer block at multiple places, and actually it also comes outside of the transformer block. That's why it's important to define a separate class for the layer normalization when we code the GPT architecture. In the last lecture, we looked at this dummy GPT model class, and the goal here was to put all of the different components together so that you get a bird's eye view without really coding too many of these components. So, what happens in this GPT model class is that there is this forward method which takes in the input, and then we convert the input into token embeddings. We add the positional embeddings to the token embeddings. The resulting embedding vector, we add the dropout layer to it. We pass it through the transformer blocks. Then, even after it comes out from the transformer, we have a normalization layer. As I showed you, within the transformer block itself, there is a normalization layer before the attention head and after the attention head. And after we come out of the transformer block, there is another normalization layer, and then there are output processing steps and the output is returned, right? So to execute this forward method, we need to define several things. So when an instance of the dummy GPT model class is created, we define these transformer blocks, and for that we'll need to create a separate class called dummy transformer block, which will ultimately become just transformer block when we learn about what happens in the transformer. And then we also create a separate class for layer normalization. Why do we create a separate class? Because layer normalization not just happens in the transformer, otherwise we would have just written this procedure here. But as you can see, even after the input comes from the transformer, we pass it through another layer of normalization. So that's why it makes sense to define a separate class of layer normalization. In today's lecture, we are going to dive deep into this class, how to create this class, what exactly does layer normalization do, and why do we need it in the first place. So let's get started diving deep into layer normalization. Okay, so the reason layer normalization comes into the picture is that When we look at the transformer block, as you can see, number of these layers are stacked on top of each other, right? So there are huge number of parameters coming from each of these layers, and we have to train these parameters. Initially we'll initialize these parameters to random values, but through back propagation we'll train these parameters so that the next word is predicted correctly. So we need to make the training process more efficient, and that's where layer normalization becomes very important. It turns out that training deep neural networks with many layers can be challenging, predominantly due to two things. It can either lead to a vanishing gradient problem, or it can lead to an exploding gradient problem. And this leads to unstable training dynamics. So the first advantage of layer normalization is that it improves really the stability and the efficiency of neural network training. So let me zoom into this further and explain this. If you consider a deep neural network like this, you have an input layer, and then you have multiple hidden layers which are stacked together after the input layer, right? And you have the output layer. So what happens is that when you do a forward pass, so initially when the weights are initialized randomly, you do a forward pass and you get the outputs. And then what you do is that based on the gradients, you do a backward pass and you try to update these parameters. So eventually, for every of these hidden layers, you will have gradients of the loss with respect to the parameters. So when you look at every layer, think of layers as accumulating gradients. Every layer will have a certain set of gradient values which will get updated after every iteration, right? Now, since we are doing the backward pass, let's say if we want to find the gradients of this layer, the gradients of this layer will depend a lot on the output of this layer because we are doing backward pass. Let me show it with a different color. Yeah, so the output of this layers I'm showing with the red color. And if you want to find the gradients of the first layer, it depends on this red colored outputs since we are doing the backward pass. Now it turns out that if the layer output, if this layer output which I'm showing by red right now, if this is too large or this is too small, that affects the gradients. So if the layer output is too large or too small, then gradient magnitudes can become too large or too small. Now think about what will happen if gradient magnitudes become too large, let's say. So if we are back propagating and the gradient magnitude in this layer becomes too large, what will happen? When you back propagate, essentially you are multiplying different gradients together, right? So if the gradient here becomes too large, by the time we reach the first layer, the gradient would have exploded to a very large value. That's called as the gradient explosion. On the other hand, if the gradient of the last layer or one of the intermediate layers is very small, when you're propagating backwards, till the time you reach the first layer or the second layer, the gradient will become very small. What will happen when the gradient becomes very small? We will not update the parameters because the parameter updates depend on the gradient magnitude. If the gradient is too small, learning will stagnate. If the gradient is too large, will lead to an unstable learning procedure. So both small gradients and large gradients lead to unstable training dynamics. We do not want unstable training dynamics. And one reason for the unstable training dynamics is that if layer outputs themselves are very large or small, as I mentioned, layer outputs affect the gradient values. So if we control the magnitude of the layer outputs, we can ensure that the gradient magnitudes themselves do not become too large or too small. Batch normalization helps this. Batch normalization helps keep the outputs of the layers to certain specific values and prevents the magnitude of the output from being too large or too small. And that's what keeps the gradient stable, which leads to stable training dynamics. That's one of the first reasons why batch normalization, or I should call it layer normalization, there is a difference, right? So I should actually call this layer normalization. Batch normalization is something different and we'll come to that later. Today we are only going to look at layer normalization, in which the outputs coming from every layer are normalized. The second advantage of layer normalization is that it prevents this problem which is called as internal covariate shift. So what happens is that as training proceeds, the inputs to every layer can change. Let's say we look at the second layer, right? In first training iteration, the inputs can have a distribution like this. In the second training iteration, maybe the inputs are skewed. So the input distribution which every layer receives can change according to the iterations. And what that leads to is that it makes training very difficult. So if the input distribution to every layer is changing, the updating the weights becomes very hard, and that delays the convergence of the parameters, and that delays the overall solution reaching an optimal value. We don't want that. Layer normalization really helps to prevent this. Layer normalization makes sure that since we are normalizing, which means that as we'll see, the variance or the standard deviation is kept to 1, we'll make sure that the mean and standard deviation of the output from every layer is fixed. And this reduces the problem of internal covariate shift, which accelerates convergence. So there are two main reasons why layer normalization is employed. The first reason is that it keeps the training procedure stable by preventing the vanishing gradient or the exploding gradient problem. And the second major reason for using layer normalization is that it prevents or reduces the problem of internal covariate shift, and that accelerates convergence, and we get to a result faster. So that's why layer normalization is employed not just in the GPT or the LLM architecture, which we are going to see right now, but in fact, in many deep learning architectures, layer normalization is very frequently used. Okay. So, what exactly is the main idea of layer normalization? It's very simple. So, we'll look at a specific layer and we'll look at the outputs of that specific layer. And what we'll do is that we'll adjust those outputs so that they have a mean of 0 and they have a variance of 1. Let me illustrate this through a simple example. Let's say you are looking at a neural network, and these four are the outputs from one specific layer of the neural network, right? So the four outputs are x1, x2, x3, and x4. And x1 is equal to 1.1, x2 is zero point 0.8, x3 is 2.3, and x4 is 4.4. In layer normalization, what you do is you find two quantities. First, you find mean of this. So the mean will just be x1 plus x2 plus x3 plus x4 divided by 4. So in this case, it will be 2.15. And the second thing which you do is you find the variance. So the variance will be 1 by 4 because there are four quantities here. And then we'll sum up x1 minus the mean whole square plus x2 minus the mean whole square plus x3 minus the mean whole square plus x4 minus the mean whole square. So that gives us the variance value. Now what we do is we perform the normalization procedure, which means that for every variable we subtract the mean and we divide by the square root of the variance, which is the standard deviation. So x1 will be replaced by x1 minus mu divided by square root of variance. X2 will be replaced by x2 minus mu divided by square root of variance. X3 will be replaced by x3 minus mu divided by square root of variance. And x4 will be replaced by x4 minus mu divided by square root of variance. So when you do this normalization, it leads to these four values. Do you notice something about these four normalized values? If you add these together, in the numerator you will have x1 plus x2 plus x3 plus x4 minus 4 times mu. So that will be 0, which means that the mean of these normalized values is equal to 0. And if you compute the variance of these normalized values through this formula, you will see that the variance of these normalized values is actually equal to 1. That's the most important thing which you should realize, or you should understand, is that after performing the normalization procedure, the values which you get, these four values, their mean is equal to 0 and their variance is equal to 1. That's the whole idea behind normalization. The In normalization, we adjust the outputs of every layer of neural network to have mean of 0 and variance of 1. And it turns out that this simple procedure helps us in the stability in neural network training, and it also helps us reduce the problem of the internal covariate shift. So let us actually see this in code. But before that, I want to tell you where the layer normalization is used. And we discussed this at the start of the lecture, but the input is converted into an input embedding. Then we add the token embeddings, and then here, right, we feed it. Before going into the multi-head attention, we have a layer normalization layer so that the inputs to the multi-head attention are normalized. Even after the multi-head attention, there is a layer normalization layer before feeding into the neural network module within the transformer block. Remember, this blue block here is the transformer block. So the layer normalization layer appears two times here, and then it appears once more again outside the transformer. So in GPT and modern transformer architecture, layer normalization is typically applied before and after the multi-head attention module, like what we have seen over here, and it also appears once before the final output layer. And we saw this when we coded in the last lecture. Here, if you see, within the transformer block, layer normalization appears two times before and after the multi-head attention, but even before the output, it we employ it once. So overall, it appears three times. That's why we need to define a separate class of the layer normalization. This one figure which I've shown over here actually illustrates the procedure of layer normalization. Let's say we have a neural network layer. These are the five inputs to the neural network, right? And these are the six outputs of the neural network. Without the normalization, you will see that their mean is not equal to zero and their variance is not equal to one. But after we perform normalization on these layer outputs, which means that for from every output here, we are going to subtract the mean and divide by the square root of the variance. So you'll get these as the resultant values after applying layer normalization. And if you take a mean of these values, you will get that mean is equal to 0 and the variance of these values is equal to 1. This is the simple illustration which describes what happens underneath the hood for layer normalization. Now, what we are going to do is that I'm going to take you through code, and we are going to implement layer normalization first on a neural network which looks like this. And then we are going to create a separate class of layer normalization which we can integrate within our GPT architecture. So let's jump into code right now. All right. So here's the code file for layer normalization. The first thing which we are going to do is start out with a simple example to illustrate how layer normalization is implemented in practice, and then we will actually fill out this layer normalization class which we had created in the previous lecture. So let's get started. What we are doing here is that we are essentially, let me take you to the whiteboard to demonstrate what we are doing here. We'll have a simple neural network layer, and the neural network is constructed such that we have two batches of inputs. So here is batch number 1 and here is batch number 2, and each batch has five inputs. So batch number 1 has x1, x2, x3, x4, x5, and batch number 2 has x1, x2, x3, x4, h5, x5. Now here we are looking at one layer of neurons, and there are six neurons here. So when these inputs essentially pass through this first layer of neurons, we have the output which is produced, and there will be six outputs for batch number 1, which is y1, y2, y3, y4, y5, y6, and there will be six outputs for batch number 2, y1, y2, y3, y4, y5, y6. So if you look at the inputs, the shape of the inputs will be two rows and five columns, because we have two batches and each batch will have five inputs, right? Then we have a sequential layer which essentially takes in five inputs and it has six outputs. This sequential layer is this second layer which I've shown you over here, this layer of six neurons. And after every neuron here, we essentially have the ReLU activation function, so which has been mentioned over here. If you don't know what a ReLU activation function is, it's fine. For this lecture, we don't need to understand this. The output of the layer is that the layer is then applied on this input batch and we get the output. Can you try to understand why the shape of the output is like this? So here you can see that we have two rows and we have six columns. If you look at the first row, this represents the six outputs from the first batch, and if you look at the second row, this represents the six outputs from the uh, second batch. And that's what exactly being shown here: y1, y2, y6, and batch 2 has y1, y2 up till y6. So this can be y1, this is y2, this is y3, this is y6 for batch 1, and this is y1, this is y2, and this is y6 for batch number 2. Okay, so this is the layer which we have, and now what we are going to do is that after this layer we are going to apply the batch normalization. Sorry, we are going to apply the layer normalization. So here I have simply explained that we have a neural network which consists of a linear layer followed by the ReLU activation layer. To quickly illustrate what the ReLU activation function actually looks like, Take a look at this image over here. So if x is positive, the ReLU is just y equal to x. But if x is equal to negative, the ReLU is 0. So there is a non-linearity here. That's the ReLU activation function. Now what we are going to do, as I mentioned, is we are going to apply layer normalization. So the way it is applied is very similar to the hands-on example which we saw on the whiteboard over here. This example, this same thing will be applying to the first batch, and the same thing will be applying to the second batch. So what we'll be doing is that when you look at the first batch, we will do y1 minus, so y1 will be replaced by y1 minus mu divided by square root of, we write this again, divided by square root of variance. Y2 will be replaced by y2 minus mu uh, divided by square root of variance. And like this, similarly, the last output, which is y6 here, y6 will also be replaced with y6 minus mu divided by square root of variance. And first we process the first batch and then we process the second batch in a very similar manner. So now let's go to code to see how this is done. So now what we are going to do is that we have the output, which is this tensor, right? And then we are doing output dot mean dimension equal to -1. Why dimension equal to -1? Because we have to take the mean along the columns. So first we look at the first batch outputs and we want to take the mean of this. So we do output dot mean dimension equal to -1, and this keep dimension equal to true. That is very important, because if we don't include keep dimension equal to true, the returned mean would be a two-dimensional vector instead of a two into one dimensional matrix. So essentially, if you use keep dim equal to true, the output which you get for the mean is this. So the first value here corresponds to the mean of the first batch. The second value here corresponds to the mean of the second batch. Since we used keep dim equal to true, the shape of this output is that it's a matrix, or rather, yeah, it's a two into one dimensional matrix over here right now. If we did not use keep dim equal to true, this would not be a matrix. In fact, it would just be a two dimensional vector, and that's generally not good, because it's good for the dimensions to be preserved as we are doing all of these calculations. Similarly, for the variance, what we are doing is that we are taking the variance across the column for both the batches and we use keep dim equal to true, and then you print out the mean and then you print out the variance for every batch. So for the first batch of data, the mean is 0.1324. For the first batch of data, the variance is 0.0231. For the second batch of data, the mean is 0.216217, and for the second batch of data, the variance is 0.0398. So remember the two commands which we have used here: dim equal to -1, because we have to perform that operation along the columns, and keep dim equal to true, because we have to retain the dimension of the final mean and the variance matrix which we have. If we did not use keep dim equal to true, later when we subtract this mean from every individual element, it will lead to some problems. So we want to avoid that. So in this text over here, I have just explained why we used keep dim equal to true and why we use dimension equal to -1. So if you have some confusion along those lines, please read this text when I share this Google, or when I share this Jupyter notebook with you. Great. And now what we are going to do is that we are going to subtract the mean. So like over here, we are going to subtract the mean and divide by the square root of variance. So we have the output matrix which is there. We are going to subtract the mean, which is now, again, you can see the mean is also a tensor which has two rows and one column. And we are going to subtract the mean from the output and we are going to divide by the square root of variance. This is the main normalization step. So this is my output now, and the normalized layer outputs are given like this. The first row again corresponds to the normalized outputs of batch 1. The second row corresponds to the normalized outputs of batch number 2. So here I am just printing out the mean and variance of the batch 1 and batch 2. So if you look batch 1 and batch 2, so if you look at the mean, you will see that the mean of the first batch is almost close to 0. This is 10 raised to minus 8, which is really very close to 0. We can approximate it to 0. For the second batch, the mean is again very close to 10 raised to minus 8. Again, that's almost equal to 0. And if you look at the variance for both the batches, you'll see that the variance is equal to 1. Awesome. This is exactly what we wanted, right? Which means that the layers have been normalized now. So note that the value 2.9 into 10 raised to minus 8 is the scientific notation for 2.9 multiplied by 10 raised to minus 8. This value is very close to 0, but not exactly 0 due to small numerical errors. In Python, what we have is this, we can turn off the scientific mode. So currently the scientific notation is on. That's why we are getting these values which have been represented in the scientific notation. We can turn off the scientific notation and then let's print out the mean and the variance. So you'll see that the mean for both the batches is equal to 0 and the variance for both the batches is equal to 1. Great. And now we'll achieve the goal which we started out this lecture with. We want to create a class for layer normalization. What would be the output of this class? Basically, this class will take in the output of a layer and it will apply the normalization to that. So let's look at where this layer normalization step is implemented. So the layer normalization step is implemented here. The layer normalization step is implemented here. So at both of these places, when we get when the inputs are received to this block and when the input is received to this block, um, we have certain number of tokens, which is, let's say we are looking at the context size for the number of embedding vectors which we have. But the main thing which I want to point out is that the number of columns which we have is equal to the embedding size, and this is the embedding vector dimension which we are using. So for GPT-2, this embedding size is equal to 768. So when we look at the So when we look at, let's say, the first row over here, the first row corresponds to the embedding for the first token, which is an input to this layer normalization, right? So we will take the mean and we'll take the variance along the column dimension, which is 768. So we'll take the mean of all of this and take the variance and then do the normalization. Similarly, we'll do this for every single row, for the input to this layer normalization as well as the input to this layer normalization. So if you see the dimension, when an instance of this class is created, we have to pass in the embedding dimension. Why do we have to pass in the embedding dimension? Because we'll see that we are going to implement something like scale and shift. These are trainable parameters, but the size of the scale and shift will be governed by the embedding dimension, and that's the same as the input vector to the layer norm module, and that will be the same as the output vector. So the input to the layer norm module will have certain number of rows, but it will have embedding columns. The output of the layer normalization, which is norm x, will have the same dimensions as the input, because normalization does not change dimensions. And we are going to scale the output with the scale and shift. I'll come to that in a moment. So the main part of this layer normalization class is the forward method, which takes in the input which I described. So when you think of the input as having certain number of rows, but mostly focus on the number of columns, which will be the embedding dimensions. In each row, let's say we have 768 embedding dimension. So in the first step, what we do is that along the column we take the mean, exactly similar to what we actually did over here. Just keep this example in mind. Then what we do is along the column we take the variance and then we subtract the mean and then we divide by the square root of variance. Note that we have added this small variable epsilon. So this is a small constant which is added to the variance to prevent division by zero during normalization. So we don't want to divide by the square root of zero, right? So we add a small variable here which is called self dot epsilon or epsilon. So this is the output of the normalize layer normalization. But we do one more step here, which is we multiply by the scale and we multiply by the shift. So let me explain what the scale and shift are. Just like we are going to train the embedding parameters, the positional embedding parameters, the neural network parameters in the GPT architecture. The scale and shift are two trainable parameters which have the same dimension as the input that the LLM automatically adjusts during training if it is determined that doing so would improve the model's performance on the training task. So this allows the model to learn appropriate scaling and shifting that best suits the data it is processing. So you can think of it as knobs, turnable knobs or fine tuning parameters which we have added just to make sure that uh, the layer normalization proceeds smoothly. Or if we want to tweak the layer normalization a bit, we can always do it with this scale and with this shift. These are trainable parameters, which means we don't specify the values of these parameters at the start. And remember that these scale and shift have the embedding dimension, so that we can multiply the scale and the output of the normalization layer together. So remember, when you look at each row has 768 dimensions, right? Or the embedding dimensions. And this self dot scale is again a vector which has embedding dimensions. So you can do element wise multiplication here, and then you can do an element wise addition here. And the epsilon parameter is set to a small value such as 10 raised to minus 5. But the main step which is being performed in this normalization layer is that we take the input, and then every row of the input we subtract the mean and divide by the square root of variance, so that the mean of the resultant row is 0 and the standard deviation or the variance is equal to 1. That's it. This is the layer normalization class. And when we bring all the elements of the GPT architecture together, we'll see that we'll replace this dummy class now with the layer normalization class which we just defined. I just have one small note towards the end, which is regarding biased variance. So, in our variance calculation method, we have opted for an implementation detail by setting unbiased equal to false. So, here. So, you might be thinking, what happens if unbiased equal to true, right? If unbiased equal to true, we'll apply something which is known as Bessel's correction. And in Bessel's correction, when we do the variance calculation, we divide by n minus 1 instead of dividing by n like what we did right now. So if you look at this implementation which I did on the whiteboard, to calculate the variance, I'm dividing by n, right, which is the um, number of inputs. If we do the Bessel's correction, we divide by n minus 1. So this 4 is replaced by 3. This does not matter too much in the case of large language models where the embedding dimension n is so large that the difference between n and n minus 1 is practically negligible. If you are interested to learn about Bessel's correction, there are many good articles on this, and you will see that it's the use of n minus 1 instead of n in the formula for sample variance, and that leads to an unbiased variance. But for now, it totally works for us if we set the unbiased equal to false. It does not lead to too much of a difference. So the reason we choose this approach is to ensure compatibility with GPT-2 models normalization layers, and it reflects TensorFlow's default behavior, which is to set unbiased equal to false. This was actually what was used to implement the original GPT-2 model, and that's why we are also using unbiased equal to false over here. So now that we have defined a class for layer normalization, let's try the layer normalization in practice and apply it to the batch input, right? So we have defined this batch over here. Let's try to pass in this batch through the layer normalization layer. So I'm defining a layer normalization class. I'm creating an instance of it. And as I told you over here, we need to pass in the embedding dimension, right? So I'm saying that the embedding dimension is equal to 5. So I'm taking in batch example. So let's see where batch example has been defined. Yeah. So this is the batch example. I'm taking in this example, and then what I'm doing is that I am applying the layer normalization layer to this batch, and then it will do all of the steps which I have mentioned over here. First, it will find the mean over all the dimensions, and then it will essentially find the variance. It will subtract the mean and then divide by square root of variance. So let me go to the batch example again and tell you what it's going to do. Let me print out the batch example actually right over here. So if you print out print out the batch example, you will see that it's this, right? So what this layer normalization will do is that it will first take the mean of this, subtract mean from all of these elements, and divide all of these elements by square root of the variance of this first batch. Then it will do the same for the second batch, and then when you get the mean and the variance of the resulting output, so output underscore ln is my resulting output, and if you get the mean and the variance, you'll see that the mean for both the batches is 0, and the standard deviation or the variance for both the batches is equal to 1. So as we can clearly see based on the results, the layer normalization code works as expected and normalizes the value of each of the two inputs such that they have a mean of 0 and variance of 1. So I hope you have understood this concept. I tried to explain this through whiteboard as well as through code, and I hope that you have understood the basics as well as the coding aspect of it. Now let's see what all we have learned in this lecture so far. So in this lecture, what we have learned is that we learned about layer normalization, and let's see how this fits into the context of the entire GPT architecture. So to master the GPT architecture, we need to learn all of these building blocks. In the previous lecture, we learned about the GPT backbone. In this lecture, we looked at layer normalization. In the next lecture, we are going to look at this thing called JLU activation. Then we'll look at feed forward network, and then we'll look at shortcut connections. So in separate lectures, we are going to cover all of this, and then you will see that all of this essentially comes together to teach us about the transformer block. And only then we'll be fully equipped to understand the GPT architecture. I don't think there are any other YouTube videos out there which cover the GPT architecture from scratch in so much depth. But I believe this much understanding is necessary for you to truly understand how the LLM architecture works. One last point which I need to mention is that in this lecture, sometimes I said batch normalization and then I corrected to layer normalization, right? If you also have this confusion, remember that layer and batch normalization are very different from each other. In layer normalization, we usually normalize along the feature dimension, which is the columns. And layer normalization does not depend on the batch size at all. No matter what the batch size is, we just take the output of every layer and normalize it based on the mean and the standard deviation. Batch normalization, on the other hand, we do the normalization for an entire batch. So it definitely depends on the batch size. Now, the main issue is that the available hardware typically dictates the batch size. If you don't have too powerful of a hardware, you might need to use a lower batch size. So batch normalization is not that flexible because it depends on the batch size, which depends on the available hardware. On the other hand, layer normalization is pretty flexible. It leads to more flexibility and training for it leads to more flexibility and stability for distributed training. So if you are in environments which lack resources and hardware capabilities are not there, which leads to low batches, etc., or if you don't want to care about batch size, you want the normalization to be independent of the batch size, layer normalization is much better in terms of flexibility. So don't make the error or don't make the confusion between layer normalization versus batch normalization. This brings us to the end of today's lecture. As I mentioned, in the subsequent lectures, we'll talk about JLU, we'll talk about feed forward network, and we'll also talk about shortcut connections. And then later, we'll see how all of it comes together to make the GPT architecture. Thank you so much, everyone, and I look forward to seeing you in the next lecture.